This one is slightly tricky because the contour is you need to deform it a little bit differently, different than our usual case. This one is okay. Ask you to use the Fourier sine and Fourier cosine. You don't have to. You can just use the full Fourier transform because cosine and sines are the real and imaginary part of the exponential function. So you can simply just use the exponential function. Just try the exponential function and just the integral first and just figure out the coefficient later. So we have the 1/2 in the denominator and cosine, and combine the two becomes e to the I x times t dx. Right. That is the function, the integral. Okay. And obviously you want to do a complex integral. So you want change to evaluate at z. This is like integrate along the real axis. And first we determine that the integral is well behaved at 0. Although there's x to the 1/2, when you integrate that, you bring the x to the square root x in the numerator, and evaluate at 0 is finite at the origin. So it's not divergent at 0. And also it's also be well behaved at the infinity. So that the argument is you have this exponential function, so that will make it convergent at large x. So so that's, and then this is a branch point, but then you probably won't need to worry about the branch cut because the contour will not contain the branch cut, so you can cut anyway. It doesn't matter. And the most convenient way to cut it is you connect a big circle, but this big circle obviously also depends on the sign of t, but if we assume t is positive, I think that is what is assumed. Because later on you will have t to the 1/2 on the right-hand side, and it's defined, I mean, those are real numbers, so you define those for positive x. Right. For positive t. So the t for t is positive. Likewise, just like the Jordan lemma, you can close it on the upper plane, right? Because x becomes z, and the imaginary part is positive over here, but then your I times I is negative, so you close it on the upper plane. So you can do that, but for us, we are not going all the way on. We are just going to half, I mean, 1/4 of a circle. But still can do that. It's the same Jordan lemma apply to part of the big circle, and then you go back from here to here. And in principle, you need to exclude this singularity out, so you cut out a little circle closer to the origin. But then you can make a simple argument that the integration along this little circle is 0. We make the argument quite a few times in all those contour, like whatever that we have a band cut go around that common contour. You make the argument already, so you know that The little circle doesn't contribute. The big circle doesn't contribute. So this plus that is 0 because there's no singularity inside. And now you want to transform that. The basically is saying integrating. This integration is along the real axis. It's like integrating along the imagined axis. So integrating 0 to real infinity is the same as integrating 0 to past imaginary infinity. Is that okay? Yeah, that. So you can change that. Change it to integration along the imaginary, partial imaginary axis. And along the imaginary axis, C is Ix. Or Iy, it doesn't matter. If you like, let's change Iy, just nothing less confusing. Okay, so this is along the axis, this is along the imaginary axis. So that x becomes z, z is Iy. One panic. Obviously, you figure out the I, what the phase angle of I. So because the branch cut is over here, you can define your branches from 0 or minus pi to pi. So this would be 0. This would be pi over 2. So this would be I would be pi over 2. E to the I pi over 2. Okay. And the same as e to the I. Z becomes I. D. X becomes dx becomes dz is I dy. And y is from 0 to infinity. Okay. Now you figure out what to do. Now again, this is you pull out. So I becomes this I is e to the I pi 2, right? And then take another square root to 1/2 factor, and it's in the denominator, so it's e minus I 4. Okay. And then you have another I. Those I's are this I's are I times, so you have another e to the I by 2. This is this I, right? And then the rest is dy, 1/2, and e to the minus y. Okay, and now this integral is totally real, right? Because y is we already defined it as the imaginary part of z, so that is real. Okay, and all you need to do is evaluate that and then to figure out this phase. The phase is just pi over 2 minus pi over 4 is I pi over 4. So basically, cancel this pi over 4. Okay, and how about this integral? This become more elementary than this one. You can either look up or this is a gamma function. Yeah, but unfortunately, we changed the order different from the text order of text. Gamma function. We'll go through that probably next semester, chapter 13. But you can use other elementary method, right? Say, most likely you can change that to a Gaussian integral. Say y change to whatever you want to call it. Change y equals to well, Cosine square, or whatever you want to call it. So dy is 2. Okay, that's this part. Why did one have just minus t? Put it here. And this cancel. So and the limit is still 0 to infinity. Oh, this 2, you can use the factor of 2 to change it to minus infinity to infinity because this is an even function. Okay, and this is a Gaussian integral, right? I mean, you know what it is. Say that again. Square root of pi over t probably, right? Because the dimension is, you can see the dimension. This is dimensionless, so you can see is of the dimension of 1 square root of t. So you capture t here. And so let me check whether we get the answer of the textbook. Okay, so this integral is square root of pi over t, and this is e to the I pi over 4, which is if you have unit circle, so that would be this point. And so this is 1. This obviously is, this is 1. And so this will be 1 over square root of 2. Right. So this is 1 over square root of 2 plus 1 over square root of 2 square root of pi over t. Okay. So the real part and the imaginary both are, square root of pi over 2t. And that's the integral, just the integral, and then multiply by whatever the coefficient is in front. So I ask you to show that, well, or you can multiply the rest because the right-hand side is just 1 over square root of t. Take the question. So both the imaginary part and real part has the factor of square root of pi over 2 in front. So you multiply by square root of 2 over pi to the other side, which is the factor in front of the left-hand side. And the right-hand side square of 1 over square root of 2. And that is for both real and imaginary part. The real part is cosine, the imaginary part is sine. Okay, so you see that this equals that we give you the required answer in the question. Can you follow all this? Well, I'm just figuring out what the value. This phase factor. This is of the magnitude of 1, right? This obviously is on the unit circle. I just figure out what the angle is and what the really imaginary part of that. Or you can take this cosine pi over 2, sine pi over 4, sine pi over 4. There's a different way to figure it out. I just use the Pythagorean theorem to try to figure that out. Okay. Yeah.
We don't need to find for the real part because it's in the branch circle, the real axis.
This one?
Yeah, that line. We don't need to find for that.
To find this one?
Yeah, we don't need to find that because in the loop, due to the lemma, the bigger circle will be 0 and the smaller will be 0. But is the horizontal line 0?
Horizontal line?
Yeah, that line.
This part? This?
No, after that.
After this one?
Yeah.
This is not, this is this one. You integrate along this one is this one. So the whole loop is 0 because it's analytic over in the inside the contour, right? So the whole thing is 0. The little circle is 0. The big circle is 0. So this is equals to this. This plus this is 0. So this going over the real axis is the same as going along the imaginary. So this is going along the imaginary axis. Okay. And then the rest is just to evaluate this real integral. Okay. And that is, you can use elementary method. Is okay? So, what else? Do you have question on homework?
One more question.
Yeah. I did it wrong. See this one?
You just worded the 2 factor.
This 2 factor
Minus infinity
The minus infinity, I changed. I erased that. I have to get habit of erasing things and instead of writing another line. Originally 0 to infinity. That's a factor of 2. So I extended to minus infinity because I usually memorize the Gaussian integral from minus infinity to infinity, which is, I mean, from 0 to infinity is just 1/2. Yeah. But I just use the factor of 2 to make it to the standard form of the Gaussian integral. Okay.
I didn't know.
Yeah, I go through too quickly. I just erase it. Yeah. I mean, it's just saving some writing on the back. Okay. What did I get? Uh, you mean the same question, right? What is your question? Self-reciprocal. Okay. Self-reciprocal. This is like a sine cosine transform. If you do an inverse transform, you get exactly the same because this is like transforming 1/x, right? And then multiply by 2/pi is the coefficient defined in the formula for doing Fourier sine transform, and Fourier cosine transform. I don't think your text will actually write it down, but that you can figure that out is the same. So this means that, so like on your textbook, the first equation is like the Fourier cosine transform minus 1/2 cosine x3 x is equals to t to the minus 1/2. Right. This is the Fourier. This is to calculate the Fourier cosine transform. This is the Fourier cosine transform of this one. Then the inverse transform will be exactly the same. Now it's dt. This, yeah, that's just the name. Right. So the transform and the inverse transform is of the same form. Yeah, the sign is also you use the Fourier sine transform. It's also exactly the same form. And part B should be elementary. This is just redefining the variable. So, it's okay. So part B should be just use whatever the integral in part A is just like doing a change of variable. Okay.